Now we're going to talk about hypothesis testing, which is also something you guys uh, will do in your in the report of your data gathering, and it's also something that's very interesting to know whenever you're doing any kind of quantitative data analysis. And actually, the idea is very much, let's say, connected to the idea of a confidence interval, and that's why we started with a confidence interval so that you get a little bit of a understanding or a intuition of the confidence interval, because there's a lot of similarities between them. But the number one thing that's important to know about the confidence interval that we're going to try to like compensate for in hypothesis testing is that with uh, the confidence interval does not give us a clear estimate of where the true population mean is, right? So we know that it is somewhere in between two different values based on how many standard errors they are away from the center of the distribution, right? So the farther away, the the less the probability that something happens. However, what it cannot tell us where it is, but it for sure can tell us where it probably is not. So the idea about hypothesis testing is that you're gonna try to find out whether, given the hypothesis that you have, if the data that you observed is really unlikely, and by really or very unlikely, I mean anything that is beyond, for example, two standard deviations or two standard errors away from the center. So anything that's to the left of this lower limit or to the right of this upper limit is very unlikely to happen. So for example, in this case, we have 2.5% of outliers, so to speak, at both sides, right? And that's because we know that 95% of the everything that happens within this within the between the lower limit and the upper limit. So if 95% is here, then 5% must be outside of that. And since the distribution is symmetric, it's equal to the left and to the right, then we assume that there is 2.5% of outliers to the left and 2.5% of outliers to the right. What does it mean to be 2.5% of outliers? It means these are the 2.5% less likely things to happen given this confidence interval that we built. And on to the right here is also the 2.5% less likely to happen in terms of high values. And at this side, it's 2.5% less likely to happen at the lower end of the values. The smaller ones, the smallest and the largest, such that they're so big that it probably doesn't happen very often. But as I position here, like the population mean, this could be the true population mean, but who knows? We don't know. It could be here, it could be here, it could be anywhere inside this interval. It could be also outside here, but it's very unlikely. So that's why when we do hypothesis testing or when we do anything in quantitative data analysis with statistics, what we are trying to give is a good probability that that thing will not happen. But we can never say like it's for sure not, because it could be, but we just want to try to be as safe as possible. So we rule out things that are not likely to happen. So as a recap, hypothesis testing, the first thing you do in hypothesis testing is you establish the null hypothesis, right? Which is the hypothesis you think is not true. And the reason now I think it's easy to understand, a little bit easier at least to understand, why is it that we come up with a null hypothesis and not with the hypothesis that we want to prove? And that is because, again, if we think of in terms of a confidence interval, we are not able to say, look, this is where the population mean is, or this is where it is. So it's not easy for me to tell you, yeah, your hypothesis, let's say you don't have a null hypothesis. Let's say you have an actual hypothesis that you think is true. I won't be able to tell you if it is true or not. However, on the other hand, if you have a null hypothesis, the one that you think is not true, and it so happens that that null hypothesis ends up being very far away from the center of the distribution, then I can say, well, you know what, that null hypothesis is not very likely to happen. And that is a good thing because you took someone that you thought was not true, and then you actually show, yeah, actually, that thing is very unlikely to happen. So unlikely that I'm confident or I feel safe in rejecting it and saying that it's not true. And so that's more or less how that's more or less the intuition between the idea of having a null hypothesis and not an actual hypothesis that you want to prove. And in general, it's because we can't prove anything. We can only disprove things that we can say that for sure are not likely to happen. But now we're gonna give like a little bit of a twist on the confidence interval. It stays more or less the same, but we're gonna move it a little bit because the hypothesis test actually consists not on asking if the null hypothesis is likely to happen given the confidence interval that we have. It's actually the opposite. We're gonna assume that the null hypothesis is true. So let's say, okay, assume it's true because I'm giving it as a hypothesis. So let's say it's true. What is the probability that my sample would have occurred? So what's the if given that the null hypothesis was true, let's say it is. If I build a confidence interval not around my sample, but around the actual the assumed hypothesis. Let's say, okay, let's just build this imaginary confidence interval, but not around my measured sample, around the actual null hypothesis. Let's say assume that is true, so we assume that that confidence interval exists. What is the probability that my sample or my sample mean in this case would have occurred? So what's the probability that I would have observed this thing that I observed given that the null hypothesis was true? And then if the probability is very low, so lower than a certain predefined significance level, then we reject our null hypothesis because we say, look, it's not likely that this mean that I observed, this actual data that I observed, it's not likely that it would happen if given that the null hypothesis was true. So probably the null hypothesis is not true. So you have to come up with some other hypothesis. And actually, most of the places where you read, you will see that hypothesis testing like this and with the actual confidence interval, they're more or less equivalent. So it's just a little bit of let's say philosophical difference, but they kind of like more or less end up being the same. But for let's say the formal hypothesis testing, we're actually going to move this confidence interval. So let me go through this again. You're still building in confidence interval as you were before, but instead of using your observed mean as the center of this confidence interval, you're actually gonna pretend that the center of the confidence interval is not your observed mean. Instead, it is your null hypothesis. So you're gonna assume that. And then you're given that you're gonna compute whether you're gonna try to find whether your observed data is too far away from that. So if your observed data actually falls, uh, yeah, let's go back here. No. Yeah. Okay. So if you're observed, if you believe that okay, this is where the assumed population mean is, if my observed sample falls very far away from that, so in this area or in this area, then I say, look, this assumption is probably not correct because it would be so unlikely that I would have actually observed this thing that I observed that this hypothesis is probably not likely to be true, right? And this is what I am trying to illustrate here in this figure. In this case, it's the same thing. It's a confidence interval. It has been built, but it has been built around the hypothesis. So you compute the standard error in the same way that we've seen before, like this let's say width of this curve, right? In order to compute 2 times to the left, 2 times to the right, it's the same thing. It's the same standard error. However, the center now is centered around the null hypothesis and not around the actual value that you observed. And as you can see here, these are the more likely observations. These are the things that we've seen before already. The things that are closer to the center, they're more likely to be observed. Like yeah, it's something that, well, if you see that, then say, yeah, it makes sense. Then there are the very unlikely observations, which are those who are far away from the center. Again, very unlikely observations. And let's say that you have this as an observed data point. So this is your mean. Suppose that you compute this confidence interval around the null hypothesis. Let's say that you measured something, and then this is what you measured. This little point here. This is your actually sample mean, right? So it's a little bit far away from the center, from the null hypothesis. Your p-value, and this is a very important concept because you will see that everywhere. Your p-value, p comes from probability. What is the probability that I would have observed this thing given this imaginary confidence interval that I just built around the null hypothesis? What's the probability of this thing here that I observed? This is like the simple mean. The p-value is let's say equivalence to this region here of the curve. And then you might think, well, why this region and not just this observed data point? Why not just the probability of this thing, right? That would make sense. However, the truth is that, first of all, because when you have a confidence interval here, in theory, you cannot compute the probability of just one point because it's a continuous value. So you always have to compute regions of the curve, but you could have established a smaller region around the observed data point or something like that. But the idea is that you want to know the probability of anything of what you observed, or something that's more extreme than that. Because if it's more extreme than that, if it's even less likely to happen than your observed data point, then it also means that, well, if something, the probability of seeing that or something even worse, that's where you define like let's say, the probability that you're going to compare with the actual null hypothesis. Because if something is even farther away from your observed data point, then it makes let's say, it makes your null hypothesis look even less likely. That let's put it this way. So if you observe that thing, or even something even worse than that, then that's even worse for let's say, gives an even worse look at your hypothesis. So that's what we're going to always keep think about. It's the probability of seeing. So the p-value, in summary, is the probability of observing the data point that you have observed, or something even worse. So if that p, and then basically the final result of a hypothesis test is that, okay, if my p-value, this probability of getting something that I observed or even worse, if that is very low, like always remember, p is probability, so low probability is bad. If the p-value is very low, so low that it makes it unlikely, then that looks bad for your hypothesis. Your hypothesis looks quite weird. You can think of many different many different examples for this. Like, for example, let's say you assume a hypothesis that, I'm just going to use an example from the data gathering, one of the data gathering that you guys are doing. Like, for example, I assume, I know hypothesis that an LNU student on average buys, let's say, 3 cups of coffee on Press Bidon every day. Now, let's say you go there and you measure, and then you see one person comes and buys 1 cup, and then the other person comes and buys 1 cup, and then you very rarely observe the same person coming in and buying another cup, let's say. So most of the time it's either 0 or 1 cup of coffee. So that, since your hypothesis is that on average people buy 3 of them, so you see how you observe the data that you have kind of makes your hypothesis look weird. Because if your hypothesis is really 3, so if your confidence interval is really centered around 3, then the probability of observing a mean of 0.5 or a 1, well, in that case would be to this side here. The probability of seeing something that's like 0.5 or 1, that probability becomes very small. So then you can say, look, my hypothesis kind of looks weird because actually assuming that it's true, the data that I just observed would not happen, or it would happen very, 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 very rarely. So then I'm ready to reject my null hypothesis, okay? Summary, you compute your p-value you build your confidence interval around the null hypothesis, take your observed data point and compute your p-value, which basically is the probability that your observed data point would happen or something worse. Then you compare that p-value with something you have established before, like 1% or 5%. If your p-value is below that, is less than that, then you say, I reject my null hypothesis because my null hypothesis is probably wrong. If not, if it's larger, if your p-value is, let's say you defined your confidence interval to 5% and your p-value is actually 8%, then you say, I cannot, I cannot decide anything about this because 8% is more likely than 5%. So it's within the central region. Let's say it's relatively likely to happen. So I cannot say anything about my null hypothesis. It could be this. It could be something else, as long as this other something else is also makes it so that my observed data point would be also likely to happen. So it could be this one. It could be another one. I cannot say. I cannot say that my null hypothesis is likely. I will not say that. I will only say, given the data that I gathered, I could not reject my null hypothesis. So it may be true, but it may also not be true. I cannot decide. Now, if you look at this, then you might be thinking, okay, well, I know how to build a confidence interval using the standard error. I know how to build it around the null hypothesis because I can build it around anything, right? It's just, I just put it on the mean so that I can take like -2 times the standard error or +2 times the standard error around whatever value I want to use. So it could be the null hypothesis. But I don't know how to compute the p-value because given a certain observed data point here, I have no idea how to determine what's the probability that that point happened or something worse. So I don't know how to compute this region here, right? And of course, the cool thing here, again, as we've seen before, is that the confidence interval is normal or approximately normal. And the cool thing about a normal distribution is that if you have the center and you have the standard error, then you have everything. You don't need anything else. The whole curve here, this whole bell curve is determined, is like a mathematical function that's based on the middle value and the standard error. As soon as you have these two things, you have everything. You don't have to do anything else in order to determine a probability. Of course, you're not going to do it by hand. There are computers that will compute that to you, and actually there's another manual method that I'm going to show you in the next slide. But the important part to know is that every time you have a normal distribution, you can determine the probability of any region under that curve. So for example, let's use this example here, like assume that IQs are normally distributed. So this is like distribution of IQ. There's a lot of people with average IQ around 100. And then the standard deviation of this curve is 16. So, you know, most people are within 16 or 32, let's say. 95% of the people in the world are between 68 or 132, right? And then, of course, there are the outliers, people who have an IQ less than 68 or more than 132. That can happen. It's not impossible, but it's very unlikely. So this is you know, again, this idea that I guess you guys got by now of normal distribution, where the things in the middle are likely and everything that's outside of that happens, but it's unlikely to happen. So then, given that, again, given that it's centered on 100 and has a standard deviation of 16, then everything else can be computed from that. So for example, if I ask you a question, what is the probability of an IQ less than 90? And this is how we usually represent that. The P of X equal less than or equal to 90, right? And there's an answer, 26.43% or 0.2643. Now, you're not going to compute this. This is something that the computer is going to give it to you, or you're going to look at it in a table, as we'll see later. What is important from this slide for you guys to know is that I have a normal distribution. As soon as I have a normal distribution with a certain middle and a certain standard deviation, all the probabilities of any region is easy to compute. And why do I say a region? Because I say, what's the probability of an IQ less than 90? I didn't say equal to 90. I said less than 90. So less than 90 is this region over here all the way to the left. And I mean, you could like assume that it goes on infinitely or something. It doesn't matter. Of course it doesn't, because there's some kind of a lower level for an IQ, even if it's zero, I guess. There's still some kind of a lower end. But usually you could, in theory, you don't have to specify how far it goes to the left. It just goes a little bit more. It doesn't matter. So because we are not really, I mean, like I said, we're not going to compute it ourselves. The computer is going to do it for us, so it doesn't matter. But this is the equivalent of this region where I say the probability of IQ is less than 90. So this is what less than 90 means. Then I say, for example, what's the probability of IQ more than 140? And so PX larger than 140. And then it's this region here. So I take 140 here, and then anything else that is to the right is more than 140. And actually, in this case, it's 0.62%. So again, based on the fact that we remember that we have 100 and then we have the standard deviation of 16. So we say 95% are between 68 and 132. So you can see that 140 is more than 132, right? So it's less than 2.5% of probability for sure. And actually, you know that we can see that it is actually 0.62%. But at any rate, just from the fact that you know that 140 is larger than 132, which is 100 plus 2 times the standard deviation, then you could already assume that it is very unlikely to happen, and it's less than 2.5% chance of happening. And do you remember why I'm saying 2.5% and not 5%? It's because I took 5%, which was outside of this region of 2 standard deviations, and I divided it between the left and the right because it's symmetric. So 5% outside of the center means there's 2.5% for one side and 2.5% for the other side. So again, maybe I didn't know the probability, but I could very safely say it's less than 2.5% because of this empirical rule. And I can also just say, what's the probability of IQ between 92 and 114? Now this is, actually these two values are within the central region that we determined, right? Which was this region of 2 standard deviations, so 68 and 132. So we could already, again, just by looking at it, I could say, look, this is more than, for sure, more than 95, not more than 95%, but for sure, it is within this this region where 95% of the people would be included, right? But then I could also say, well, this is within the 1 standard deviation actual region, right? So it's, for example, 100 minus 16 would be 82. And 100 plus 16 is 116. So this is within that region, right? Because 92 is more than 80. What did I say? 82, not 82, 84. 92 is more than 84, and 113 is less than 116. So again, I could say I know that this will be less than 65%. And if you remember the empirical rule, we established that 65% of the people are within one standard deviation, right? So was it 65? No, I'm a bit confused with the exact number of the empirical rule. But we determined that it was 95% for 2 standard deviations, then it was 67 maybe or 65 for 1 standard deviation. So again, I can say, okay, I don't know exactly how much, but I know that it's less than 65% because it's within the region of 1 standard deviation. And then it ends up being 50%. But even if I said I know that it's less than, well, slightly less, let's say, than 65%, because it's slightly within the region of 1 standard deviation, and that would be like that wouldn't be so far away from the truth, right? The computer will simply give you the answer. But it's cool to have these intuitions in our mind when we think about it, because that helps us understand what's going on, right? And then I just wrote some stuff in red here, just so you understand how we compute this. It's because actually the way that you compute probabilities in the normal distribution is by using what we call cumulative probabilities. So this one here is just a very straightforward cumulative distribution, right? I say anything that's less than or equal to 90 means it comes from all the way to the left, wherever it is, wherever it stops in the left, up to 90. This is a cumulative distribution. So we say it's cumulative because, again, it comes from wherever it starts on the left, doesn't matter, until a certain number. That's a cumulative probability up to a certain number. And then in this case, it's the opposite, right? It's the cumulative to the right, but that cumulative to the right actually doesn't really exist. What you can do is you can take 1 minus the cumulative up to that point. And the reason is that, well, I don't want to go into details, but every probability distribution sums to 1. So the whole curve here has to sum to 1, because that's statistical theory. Every probability distribution must sum to 1. So if I consider that the whole curve sums to 1, then I take 1 minus the region all the way to this point, gives me the actual the rest of it. But it doesn't matter to you guys, just a curiosity. And here is here's exactly the same. Again, it's always based on cumulative distributions, because we can't have, like, we can't just compute um, whatever we want like this straight directly. You have to first compute the cumulative and then derive that. And in this case, it's also like, if you think about it, it's smart. You just take the cumulative distribution up to 114, which is from the beginning until 14, and then you take minus the cumulative distribution up to 92, which is this region here. So it's the entire region minus this region here, and then you get the actual region in the center. But this is just curiosity for you guys, just so you understand that every probability in a normal distribution is computed cumulative, always. And then you are, let's say, or the computer or whoever does that has to do this little math in order to determine that. So, okay, so this is what you need to know in order to perform a hypothesis test. Now we're going to go again and on let's say step by step on a summary of what does it mean to perform a hypothesis test in one sample. Some of you are actually going to do it in 2 samples in the data gathering that you're doing, and that will come a little bit later. But for now, the most important part is that you understand how to do a null hypothesis in 1 sample, and then we're going to derive, and let's say we're going to improve that a little bit in order to do it with 2 different data that you're trying to compare. So let's go. Summary of steps. First step, establish your null hypothesis, which is the value you might reject or you want to reject, right? Again, I like to always highlight this a ton of times because it's very important to remember. So you establish that. It's some value. It's x equals 100 or whatever. It doesn't matter. It's up to you. It's up to your study. You have to determine that. Then you choose a significance level, which we call alpha, usually 5% or 1%. If you don't have, let's say, any kind of any previous knowledge or any previous thing, you just assume it's 5% and just use 5%, because then 5% basically means, look, I am ready to reject my null hypothesis if the probability is less than 5%. Remember that the significance level determines how much you have to be like less than that in order to reject your null hypothesis, right? So if you say 5%, then that means, look, I am ready to reject my null hypothesis if the probability that it actually happens is less than 5%. Or you could say, no, actually, I want to be more conservative. I will only reject my null hypothesis if it falls below 1%. Because 5%, well, 5% is like, yeah, it's not likely, but it's 5%, right? It's not that small of an interval. So maybe you're not ready to reject your hypothesis then with less than 5%. So you might choose actually 1%. So say I'm only going to reject my hypothesis if it's really, really, really unlikely, which is less than 1% of chance of happening. It's very hard to say for sure. For your data gathering, I will say always use 5%. 5% should be fine. But there are cases where you want to use 1%, like for example, when you're testing drugs and things like that, then you want to like you have a null hypothesis that your new drug that you just came out with does not cause any dangerous collateral effects, for example. And then in that case, you only want to reject that kind of hypothesis, for example, if it's really like very, very low. Very, very low chance that's actually true. Maybe I just came up with this example. I'm not sure exactly if that's how it that would make sense. But what happens is that if you're dealing with something, let's say, that's dangerous to someone, like maybe in there's a building and you have no hypothesis of something related to the building, so you just want to reject that if you're absolutely sure that it's not the case. So then you use, like, for example, 1%. You can use like 1%. But for you guys, 5% is fine. Then the next thing is we're going to determine if your test is one-tailed or two-tailed. This is an interesting thing that you have to think about. It's very simple, but it's something you have to think about that is also part of your design, the design of your hypothesis test. So these are examples of two-tailed on the left and one-tailed on the right. So basically, what does that mean? Well, when I was talking about this thing with 2.5% at one side, 2.5% at the other side, well, yeah, we know that this 95% interval is roughly within these two standard errors away from the mean, both to the left and to the right. You'll see here that they're actually using 1.96 instead of 2, which is also something that people do. It's no, I guess I've talked about it before, so it's not really a big deal. Sometimes you can use 1.96, sometimes you can use 2. But the idea here is that, well, you have this area here with 2.5% and this one, but it's not always the case that in your specific design of your hypothesis test, it might not be the case that you're actually interested in these two sides. Because, for example, if you have a null hypothesis that, again, the people on average buy 3 cups of coffee every day on LNU students, you might be interested. Your alternative hypothesis could be that, actually, I think they buy more than 3 cups of coffee every day, so or less. This is your alternative hypothesis. Remember, this is the one that you actually think is true, but you're not testing for that. You're testing for the null one. So your null hypothesis is that the average number of cups of coffee is 3. But when you're doing the test, you have to kind of define whether it's one-tailed to the left or one-tailed to the right, or it's actually two-tailed. Because if you say, my alternative hypothesis is that they buy actually more than 3 cups of coffee every day, then you're actually looking for a one-tailed test, because you're only comparing one side of the normal, right? You're only thinking about something that happens, let's say, to well, to the right of your normal distribution. So if something is more, so in that case, what happens is that basically where I'm trying to get to is that the 95% interval that you're going to use is actually not going to include only the center part. It's actually going to include, let's say, the center plus one of the sides. And that's why it's called one tail, because then you're only interested in a one tail here. So if your value is either here or to the left, then basically you will say, well, my probability is too small, so I will reject. While on the other hand, when you're doing two-tail tests, then you're actually not interested only on, let's say, if it's less or more or greater or smaller, but you're actually just, you just care if it's different. Like, I don't know, maybe your null hypothesis is that I don't know if it's smaller or greater. All my null hypothesis is just that it is a certain value, and my alternative hypothesis is just I think it's different. I don't care if it's smaller or greater. It doesn't matter to me, but I think it's different. So I'm going to try to prove that it's not, that value is wrong. Whether it's smaller or larger, doesn't really matter to me, as long as I prove that this null hypothesis is actually wrong. And that's when you have a two-tail test. So I'm going to say that probably one-tail tests are usually more common, especially when you have these ideas of, I think that this thing is actually larger than the null hypothesis or smaller. But two-tail tests are also very common when you don't care. You just want to make sure that you reject the hypothesis, period, right? So then you have to choose, because this will affect how you compute the probabilities, right? So at first you just choose it. So just define, well, am I interested in actually showing that the actual value is to the left of the null or to the right of the null, or or do I just want to reject it? Then you choose between a two-tailed or a one-tailed test. And then we're going to see later how to actually compute the probability based on that, right? But for now, just make sure you choose one of the two. The next thing, and now we're gonna talk about the two next steps that you're gonna take, which is the first one to determine the z-score, and then to compute the p-value. And both things kind of go the same way. So that's why we're gonna do them both at the same time. First, talk about what is the z-score, and then what is the p-value. But let's just recap, right? You have your confidence interval. You build your confidence interval based on the standard error. You center your confidence interval in around the actual null hypothesis, as we've been discussing, right? We kind of like shift a little bit from the actual observed mean and going to the null hypothesis. And then next, we're going to try to determine if the probability of actually observing what you observed is very small. So that's why we're gonna determine the z-score of our sample mean. And the z-score is this thing. It's analogous to this thing where we're using either 2 or 1.96. These were z-scores actually. So z-score, if you forget about the actual equation or formula, the intuition for z-score is how many standard deviations is a certain value away from the mean. So like we were talking about, you have a certain mean, let's say it's a null hypothesis. Then if something is 2 standard deviations plus away from the mean, then that thing is very unlikely. The z-score is then just a formal definition of how much is this away from the mean. So is it 2.1? For example, if you compute the z-score and then it comes out as 2.1, then you can say, yeah, I will reject my hypothesis, because 2.1 is more than 2. So if it's more than 2 standard deviations away from the mean, or in this case, if it's 2.1 standard deviations away from the mean, then I will reject it because it's more than 2, right? And because you defined later, or if you were using 1.96 actually, which you could, then actually if you took a z-score and you compute the z-score and the z-score comes out as being like 1.98, then that's enough for you to reject your hypothesis, because say, okay, 1.98 is more than 1.96. So yeah, my value is farther away from the mean than 1.96 standard deviations. So yeah, I will reject my hypothesis. So the z-score is just this, like this formal definition of how you compute that thing, how you compute how many standard deviations you are away from the mean. And then you're going to compare that to the actual, let's say z star, as people usually say, where you define that anything beyond that is a rejection. And that's analogous to computing the p-value. We're going to talk about both. But so the formula here very quickly is just the sample mean that you have observed minus the null hypothesis. So for example, if the null hypothesis is 10 and your observed sample mean is, let's say, 13, then 13 minus 10 is 3, right? And then it's a positive value, so it's to the right. But on the other hand, if the observed sample mean was less than the hypothesis, so for example, if it was 5 and your null hypothesis was 10, then 5 minus 10 is minus 5. So that just means that it doesn't matter too much, but it means that it is to the left of your mean. So when you consider the actual, again, I have the problem here. Yeah. So again, if we consider, yeah, if you consider that you were centered here on the null hypothesis, a negative value would be a value to the left because it's less than your null hypothesis, and a positive value would be a value to the right because it's more than your null hypothesis. So you still have, they're still in this range in any way. And then it's divided by the standard error. So this thing here is just the standard errors. Remember the measured standard deviation divided by the square root of the number of points you have in your sample. So this is just the standard error. And basically that's it. It's like how much is the standard error? How much is my am I away from my mean? And then this formula here will represent that. Again, it's just more out of curiosity. You don't have to really compute that because the computer will always give it to you. And like I said, there is like this manual way of computing z-scores and p-values. Well, not z-score, because z-score is this one, but given a z-score, given that you compute a z-score, based on that z-score, you can then derive the probability. So let's say your z-score is 2.3, then there is this table, this crazy table here that will give you the probability, the cumulative probability of that happening. So for example, let's say you took this thing here and then you computed a z-value, and that's 1.35. So this is how it works here. It's kind of crazy. It's 1.3, and then you go to the left until you find the 0.05 here, for example. So this means 1.35. So let's suppose that your z-value just computed was 1.35. So you say, okay, I am my observed sample mean is 1.35 standard deviations or standard errors away from the mean. What is the probability that something like that would happen? What's the probability that this thing would happen? Well, that probability is actually 91.15%, the cumulative probability. So remember, again, the cumulative probabilities, remember that we said this is the cumulative probability. And 1.35 would be somewhere over here. So the cumulative probability, the whole thing, all the way up here, that is 91.15%. That's not the p-value, because the p-value is actually the opposite. It's 1 minus that, but it doesn't matter at this point. What matters is that this is how you compute probabilities if you wanted to compute cumulative probabilities by hand using this thing called a z-table. It doesn't matter too much. What will happen to you guys is that you're going to put this in the computer, we're going to tell you what is it. So I just wanted to make sure that you know how to interpret. You know what's happening in that when you do that. And so based on this, you can compute your p-value, because now you have the cumulative probability. And if we go back here, remember that, for example, again, if you're let's say if your test is one-tailed and you're only interested in the left tail, that's it. You don't need anything else, right? You already have it here. This is your cumulative probability. This is your p-value, and you just compare that to the significance level. If you had a one-tailed test that was to the right, so it's like this, you're testing for values that you observed or worse or larger, then you would have to actually take 1 minus the value that you got. So for example, in this case, since I got 0.9115, which is 91.15%, but I'm actually interested not in the cumulative probability to the left, but in the cumulative probability to the right, then I would take 1 minus this thing, and that would be 9.85%, right? So that will be 9.85%, and I would say, okay, there's a 9.85% probability that this thing that I saw happens or worse. And for a confidence level of 5%, that is not a rejection. So you would say, no, I cannot really reject my null hypothesis because it's larger than 5%. So be it. I don't know if it's true, but I also don't know if it's not true. And basically that's how you would compute your p-value, and then if your p-value is below your alpha, which is what we've been talking about, if, in other words, if it's so unlikely that this thing will happen that the null hypothesis is probably wrong, then you reject it. Otherwise you don't. And again, when you don't reject it, please don't say, yeah, my null hypothesis is probably right. No, we don't know that. We have absolutely no idea about whether it's right or not. All we know is that it's relatively likely to happen. So if that was true, this observed point would still be relatively likely to happen. So maybe it is, but I don't know.